Hello and welcome to Beauty at Work. We are in between seasons, so please enjoy this clip from one of our earlier episodes. Philosophers have been trying to define beauty for centuries. I'm not sure anyone's actually succeeded, but we can identify a few essential aspects of it in particular domains. In this clip, astrophysicist and author Dr. Mario Livio explains how these aspects of beauty are especially important in physics. Here's what he had to say.
To define beauty is an almost impossible task. There probably are as many definitions as the number of people you're going to ask to define it. What I tried to do in that book, and that in itself was hard enough, was to define, to try to narrow down a little bit. When does a physicist talk about a certain theory in physics specifically as being a beautiful theory? So it was not a definition of beauty. It was a definition of beautiful theories in physics. And even that turned out to be very difficult, because if you, again, look at many scientists even who talked about beauty in physics, they use many, many words like harmony and balance and all kinds of words like that. And I tried to somehow focus on the things which I thought were absolutely essential in a way. And I ended up with three concepts, as you mentioned. I mean, one was symmetry. And symmetry I put in because most of the fundamental laws of physics, they have a symmetry associated with them. In fact, all the laws that we call conservation laws, like, people heard about conservation of energy, conservation of momentum, and so on. All of those conservation laws stem from certain symmetries. For example, conservation of momentum stems from the fact that the laws of physics are symmetrical under translation, which means they don't change from place to place. We see the same laws that we have here on Earth apply in a galaxy that is 1 billion light years away. The same laws of physics apply. Conservation of energy comes from the fact that the laws are symmetric with respect to time. The laws appear not to change with time, and so on. So symmetry is really, if you like, almost the source from which laws of physics stem. So that was clearly a necessary ingredient. The second concept that I introduced was simplicity, which I meant in the sense of reductionism, namely that you want theories in physics with the minimum number of variables or equations to describe as many as possible phenomena. For example, every physicist will tell you that Maxwell's theory of electromagnetism is fantastically beautiful because with just four mathematical equations, he could explain all the classical electromagnetic phenomena. Think about this. There is so much in electromagnetism, all explainable with four equations. That is considered absolutely beautiful. Things like Einstein's theory of general relativity is thought by some to be the most beautiful theory of all. It's first of all, it has lots of symmetries built inside it, but also, with this one theory, you explain everything that's related to gravitational force, and so on, whether it is, tides in the ocean, or it is the planets moving around the sun, or how the universe as a whole behaves and all that. So all of that is there. So that was the concept of simplicity. And finally, there is the concept that probably least number of people know what that is, which I call the generalized Copernican principle. And what do I mean by that? starting from Copernicus taught us uh, that we or the Earth are nothing special. We're just another planet orbiting an ordinary star and so on. Since then, we have gone through four more, if you like, Copernican revolutions. Um, Astronomer Harlow Shapley showed that in our own Milky Way galaxy, the solar system is not at the center, is some 2/3 of the way out. So again, nothing special. After that, Edwin Hubble and others have shown that there are many galaxies. By the latest estimate, maybe as 2 trillion galaxies in the observable universe alone. Um, the Kepler Observatory has shown that there are terrestrial planets a bit like the Earth in our own galaxy, in numbers like from a few hundred million to a billion or so. So in that respect, also we're nothing special. And finally, perhaps, there are some speculative theories now, which it's called the multiverse, which maybe even our entire universe is just one member of a huge ensemble of universes and so on. So, in all of these steps, we have kind of progressed to a situation where the theory is not dependent on us being there or the Earth being in a special location. So, and we would like both theories to do that. Should mention something though. The last step which I mentioned, multiverse, that maybe there are many universes, that's maybe where Copernican humility meets its limit. Because it is possible that in these many universes, the laws of physics are different, or the values of constant of nature are different, so that, for example, complexity and life could not emerge in them. So our universe is somewhat, if this ensemble exists, our universe may be special in this ensemble, not quite the same as everything else. So, to give you a somewhat silly example, but which exemplifies this, is suppose you wake up in the morning and you wonder, what am I? Now, if you just went by statistics and by, not wanting to be special at all, you would say, I'm an insect. Because insects are the largest biomass on Earth. At any given moment, the estimate is that there are about 10 to the 19 insects. That's one followed by 19 zeros of insects. So, just speaking like that, chances are you are an insect, yes? But why is it not true? Why is it false and you are not an insect? Because merely by wondering about the question, what am I, you already distinguished yourself as being special and not an insect. Yes? So, yes, you want this generalized Copernican principle to be nothing special, but it does hit a limit at the end. So, we now hit that limit, for example, in this example.
Yeah, no, that's really fascinating. You also dismiss, I suppose, the value of elegance, which is another sort of criterion that a lot of scientists bring up as not being particularly necessary for a definition of beauty in scientific theories, right?
No, I don't dismiss it. I mean, elegance is brought a lot in mathematics. I mean, people talk about elegant proofs. There are proofs that are shorter, usually, simpler, uh, somewhat surprising, and so on. Now, in physics, I think that this concept of elegance is captured by a combination of simplicity and symmetry. So this is why I didn't bother to list it separately. But elegance is certainly something very nice to have. And in mathematics, it's there definitely are problems where the proof is more elegant this way than it is that way. You find the answer in more elegant ways, and so on. So it's an important concept, but I wanted to be as reductionist as possible in my definition. So I did not list it as a separate
Right.
necessary condition.
Yeah, you see it as a function of other, of symmetry and simplicity. Um, Tell us about your own experience, in your own career. Are there moments of encounters with beauty that stand out to you in your memory?
Well, you, not necessarily things that I have done. I mean, there are things that clearly stand out to me as I just mentioned this element of surprise. The element of surprise is very important, and well, it's captured in these other things. But yes, but it is important. By that I mean, for example, if I look at general relativity, which is this incredible theory of Einstein that describes gravity, for the life of me, I still did not understand how he thought about that. I mean, there are many things that are in the air. And, for example, special relativity, had Einstein not written it, somebody else would have within a year or two. Henri Poincaré was extremely close, to writing something like this. General relativity, yes, Hilbert was playing with some ideas like that and so on, but not so much, more in the mathematical sense, and somewhat less than Einstein's really concept of everything that there is. It wasn't in there. Similarly, I've written a book about symmetry, which was called The Equation That Couldn't Be Solved. And in it, I described this French mathematician, Évariste Galois, who died at the age of 20, but before the age of 20, he invented a branch of mathematics that today we call group theory. That was not in the air at all when he formulated it. I mean, that, really blows my mind when I see things like that. So those are the types of things that really, that's when sometimes catches you by surprise like that. I mean, those are moments that I definitely remember.
Yeah. They seem to evoke a sense of awe, I suppose, right? I mean, the fact that someone can come up with something
That's
like
right.
this.
That's right. Yeah, but in this case, I mean, there is awe from the universe itself, yes, which is so fantastically beautiful in itself. Yes, we all feel that. Yeah, you you have to look at the new images of that came from the James Webb Space Telescope, or previous images that came from the Hubble telescope, and so on, and you just realize that not only are they almost as attractive to the eye as works of art, but at the same time, they actually represent real objects in our universe, which adds to it yet another dimension. So there is that awe, and then there is the awe that what the human mind is capable of. How could this young mathematician of age by the age of 20 do that? I'm trying to think. I've had a fairly reasonable career as a scientist, but when I'm trying to think what have I done by age 20, the answer is absolutely nothing.
Yeah. Right.
This guy formulated group theory. I mean, it's
Wow.
amazing.
Yeah, it's astonishing. I mean, there's also, I suppose, that that famous Einstein quotation that the I can't remember the exact phrasing, but what is marvelous about the universe is the fact that we're able to understand it at all, right? I mean, the very fact that if you add that to your Copernican principle, given how insignificant we are in the scheme of things, it seems rather bizarre that we're capable of grasping the laws that govern everything.
Right.
Or that.
Yeah, from a physical perspective, we're insignificant. But but from the sense of what Einstein meant when he said that, we are extremely significant because you see, with every step that I mentioned, for example, with these 5 Copernican revolutions, if you like, those revolutions meant that we as humans understood something new that we didn't know before. So our mind expanded precisely as fast as our physical significance diminished. So, in that sense, we really are central to everything.
That's extraordinary. Yeah. I suppose, I mean, I wonder what you think about whether what scientists have found beautiful over the centuries has changed in that respect, right? So I suppose prior to Copernicus, maybe what might have been beautiful would have been things that established our centrality in the scheme of things, as opposed to now things that establish how decentered we are. Do you see any changes, I suppose, over the centuries in these sort of fundamental aesthetic criteria that govern science?
No, I think it is more a matter of perspective. You see, for many, many centuries, people thought that the orbits of planets around the sun have to be circles, mainly because of aesthetic reasons. When Kepler discovered that the orbits are ellipses, Galileo, the great Galileo, did not accept that because he was still also prisoner to this aesthetic idea that the orbits have to be circles. But you see, that came from a misunderstanding because the symmetry is not of the shapes. The symmetry is of the laws. The law of gravity is symmetric under rotations, which means, yes, the orbit is an ellipse, but the ellipse can have any orientation in space, and all of those are allowed. Had Galileo been taught that, I'm sure that he would have found that these ellipses are also beautiful. It was just a misunderstanding because at that time they still didn't have, the right perspective.
Yeah. Beauty at Work is brought to you by Templeton Religion Trust. If you enjoyed this clip, go check out the full episode. And please take a moment to subscribe and leave us a review. It really helps get the word out about the show. Thanks, and see you next time.